In early 2025, one Chinese company changed the global AI conversation. DeepSeek released a powerful reasoning model at a price that challenged assumptions about how expensive frontier artificial intelligence had to be. Technology stocks moved. Silicon Valley took notice. And for many people outside China, the country's AI industry suddenly appeared from nowhere. But DeepSeek was not the beginning of Chinese AI. And in 2026, it is no longer the whole story. In the space of a few weeks, China produced a new generation of systems. Moonshot AI's enormous Kimi K3, DeepSeek's updated V4 Flash, and MiniMax H3, an open-weight video model that can create high-resolution clips with sound. At the same time, companies are moving beyond chatbots toward agents that operate software, humanoid robots that learn physical tasks, and domestic computing systems designed to reduce dependence on American chips. The important change is not that one Chinese model has beaten one American model on one benchmark. Benchmarks change. Rankings move. Company claims need independent testing. The real change is structural. China is building an AI ecosystem optimized around open weights, falling prices, rapid product deployment, manufacturing, and scale. Its weaknesses, advanced chips, software compatibility, energy efficiency, safety, and commercial profitability, remain serious. But its strengths are becoming impossible to dismiss. So what can China's newest AI systems actually do? Why are companies releasing such large models? How close are Chinese robots to useful work? And what does all of this mean for the global AI race? Today, we are going beyond the headlines to examine the latest AI developments in China as of August 2026. The latest AI developments in China, beyond the DeepSeek moment. The most dramatic recent release comes from Moonshot AI, a Beijing startup founded in 2023. Its new flagship, Kimi K3, contains 8 trillion parameters. Moonshot describes it as the first open-weight model in the 3 trillion parameter class. It has native vision, can process text, images, and video, and supports a context window of up to 1 million tokens. That number sounds absurdly large, so we need to explain what it means. Parameters are adjustable values learned during training. They are not the same as facts, memories, or brain cells, and more parameters do not automatically produce a better model. Kimi K3 also does not activate all 8 trillion parameters for every word it generates. It uses a mixture of experts' architecture. Imagine hundreds of specialist neural networks inside one larger system. For each piece of input, a routing mechanism selects a small group of relevant experts. Moonshot says K3 activates 16 experts out of 896 for each token. That allows the model to contain enormous total capacity without paying the full computational cost on every step. What is the model designed to do? Not simply answer questions. Moonshot emphasizes long-horizon coding and agentic work. K3 can examine large software repositories, use terminal tools, write and test code, research across documents, analyze visual material, and continue multi-step tasks with less supervision than an ordinary chatbot. Its million-token context window could hold a huge codebase, a collection of reports, or many hours of transcribed information. In theory, this gives the model a larger workspace and reduces the need to break information into tiny pieces. But context size should not be confused with perfect memory. A model may accept 1 million tokens while still overlooking important details, becoming distracted, or making errors across a long task. The ability to fit information through the door does not guarantee that the model understands everything inside the room. Kimi K3 has performed strongly on coding and agent benchmarks, and it reached the top of public ranking for front-end coding shortly after release. But Moonshot's own technical report also acknowledges that the model's overall performance still trails the most powerful proprietary systems in some evaluations. That honesty reveals why K3 matters. It does not need to be the undisputed best model in the world. It needs to be good enough, accessible enough, and modifiable enough to make frontier capability less exclusive. Kimi K3 is often described as open source. The more accurate term is open weight. The distinction matters. Model weights are the learned numerical components of a trained system. If weights are available, researchers and companies can download the model, run it on their own infrastructure, modify it, fine-tune it, and study its behavior, subject to the license and enormous hardware requirements. But full open source would imply much more. Transparent training data, complete training code, detailed filtering methods, reproducible pipelines, and a license meeting widely accepted open-source definitions. Most so-called open AI models, Chinese or Western, do not provide all of that. Kimi K3's weights are public under Moonshot's own license, but the entire recipe is not. MiniMax H3 has also released weights with specific usage conditions. DeepSeek publishes model cards and technical information, but not every ingredient needed to recreate its systems from the beginning. Still, open weights have powerful consequences. A university can investigate failure modes without sending private data to an external API. A company can deploy a model behind its own firewall. Developers can adapt a Chinese model to Arabic, Indonesian, Spanish, or a specialized scientific field. Countries that do not want their AI infrastructure controlled by a small number of American companies gain alternatives. There is a security trade-off. Open weights can support research and local control, but they can also make safeguards easier to remove. Powerful coding systems can be used for defense, productivity, or cyber attacks. Openness distributes capability faster than governance can distribute responsibility. China's open weight strategy is therefore both technical and geopolitical. It gives Chinese companies a way to build global developer influence even when their consumer chatbots face trust, regulatory, or branding barriers overseas. If Kimi K3 represents scale, DeepSeek represents economic pressure. DeepSeek released its V4 generation in April 2026, including a larger Pro model and a smaller, faster Flash version. At the end of July, the company updated V4 Flash with new post-training, strengthening a system already designed for coding, reasoning, and long-context work. The headline is not only performance, it is price. DeepSeek has repeatedly pushed API costs below those of many international competitors. Prices can change quickly, promotions complicate comparisons, and the real cost of completing a task depends on speed, errors, and how many tokens the model consumes. A cheap model that fails 3 times may cost more than an expensive model that succeeds once. Even so, DeepSeek has forced the industry to confront a possibility. Advanced language intelligence may become a commodity faster than expected. For developer, falling token prices change which products are practical. A customer support system can examine every conversation. A coding agent can test several possible solutions. A factory can summarize data from thousands of sensors. A small business can automate paperwork that once required custom software. Low prices also change model behavior. If intelligence is expensive, applications ask the model one careful question. If intelligence becomes cheap, applications can deploy many agents, allow them to debate, verify one another, or repeat a task until confidence improves. This is part of China's broader competitive method. Make a capable product inexpensive, scale the market, and force every rival to become more efficient. The danger is that price wars can destroy companies as well as margins. Training and serving large models still require capital, electricity, engineering, and scarce hardware. If users expect intelligence to cost almost nothing, AI labs must find revenue through cloud services, enterprise contracts, advertising, devices, or vertical applications. The race towards zero is exciting for users. It may be brutal for the companies running it. Language models are only one front. At the end of July, Shanghai-based MiniMax introduced H3, a multimodal video generation system. The model can interpret combinations of text, images, video, and audio, then generate clips with native stereo sound at resolutions reaching 2K and durations of up to 15 seconds in its hosted system. The phrase, native sound, is important. Earlier AI video workflows often generated silent images first, then added speech, effects, or music through separate tools. That separation could create mismatched lip movement, weak timing, and sound that felt pasted onto the scene. A system trained to reason across sight and sound can attempt them together. A door slam can occur at the moment of impact. A voice can belong to a visible speaker. Music can react to a cut. Off-screen sound can imply something outside the frame. H3 supports text-to-video, image-guided generation, reference-based control, and continuation from existing audiovisual material. MiniMax released model weights in early August, allowing independent developers to experiment locally, although the released components and license do not make every part of the commercial production pipeline completely open. What can people use it for? Advertising concepts, storyboards, game cinematics, music videos, educational scenes, product visualization, and early film pre-production are obvious examples. A small team can test 10 visual ideas before paying for a physical shoot. A creator can produce material that once required actors, locations, cameras, editors, and sound design. But 15 seconds of impressive video is not the same as a coherent film. Long-form storytelling requires consistent characters, geography, props, causality, performance, editing, and emotional progression across many shots. AI video still makes continuity errors, misunderstands physics, invents details, and can fail in ways that are difficult to correct precisely. It also creates urgent problems around consent, copyright, performer identity, and misinformation. H3 is not the end of filmmaking. It is evidence that the boundary between generating an image and generating a complete audiovisual moment is disappearing. Focusing only on Kimi, DeepSeek, and MiniMax would repeat the mistake of treating Chinese AI as a story about one surprise company. Alibaba's Qwen family, Zi's GLM models, ByteDance's systems, Baidu's Ernie platform, Tencent's Hunyuan, Meituan's Longcat, and models from major universities all contribute to a crowded market. On August 3, Alibaba officially released the hosted version of Qwen 3.8 Max, a 2.4 trillion parameter mixture of experts model aimed at coding and professional work. Alibaba said open weights for both the flagship and a smaller 27 billion parameter version would follow. As of this script's August 7 cutoff, that promised weight release was still a future event, not something we should report as already completed. Different companies have different advantages. Alibaba owns cloud infrastructure and e-commerce networks. ByteDance understands recommendation, video, and consumer distribution. Tencent controls major communication, gaming, and enterprise platforms. Baidu has search, autonomous driving research, and cloud services. Startups such as Moonshot, DeepSeek, Z, AI, and MiniMax can move faster and concentrate on frontier models. This competition produces rapid releases, aggressive pricing, and many open weights. It also creates duplication. Companies train similar systems, chase the same benchmarks, and spend heavily without proving durable business models. Consolidation is likely. Some labs may become infrastructure providers. Others may specialize in coding, media, robotics, medicine, or finance. The winner may not be the company with the largest model. It may be the one that embeds AI most deeply into a service people already use. That leads to the most important transition in 2026. The move from models that speak to systems that act. A chatbot waits for a message and returns a response. An agent receives a goal, creates a plan, uses tools, remembers intermediate results, and takes multiple actions. Instead of asking, "How should I compare these suppliers?" a user might ask an agent to collect quotations, normalize the specifications, identify risks, build a spreadsheet, and prepare a recommendation. Instead of requesting a piece of code, a developer might ask an agent to inspect a repository, reproduce a bug, edit several files, run tests, and document the change. This is why recent Chinese models emphasize long context, tool use, coding, and multi-step reasoning. The valuable unit is no longer the answer. It is the completed workflow. China is also building infrastructure around agents. In 2026, authorities issued guidelines defining AI agents as systems capable of autonomous perception, memory, decision-making, interaction, and execution. National standards followed, covering agent identity, discovery, communication, and external tool invocation. That sounds bureaucratic, but interoperability could matter enormously. Imagine agents from different companies trying to exchange information, identify one another, request services, and prove what they are authorized to do. Without common protocols, each platform becomes a closed island. With standards, agents could form an ecosystem more like the web. The risk is obvious. A chatbot can give bad advice. An agent can act on it. It can delete a file, leak information, purchase the wrong product, follow a malicious instruction hidden in a web page, or make hundreds of small errors at machine speed. Useful agents therefore require permission boundaries, identity, logs, verification, secure tool access, and clear moments when a human must approve an action. Autonomy is not one switch. It is a carefully designed ladder of authority. Software agents operate computers. Embodied agents operate the physical world. China may have a special advantage here because it combines AI research with the world's largest manufacturing ecosystem. Robots require motors, gearboxes, batteries, cameras, sensors, precision parts, factories, supply chains, and places to test real work. China already produces many of these components at scale. Unitree, Augibot, Ubtech, Galbot, and a growing field of competitors are turning humanoid robots from spectacular demonstrations into early industrial products. In February 2026, Unitree unveiled an embodied intelligence model and said it was being tested in the company's own factory, where robots could participate in assembling other robots. In March, it released a real-world teleoperation dataset designed to help humanoids learn diverse full-body tasks. The combination is important. A robot body without a general model can execute scripted routines, but struggles when objects move or conditions change. A powerful model without physical data may speak fluently while failing to pick up a tool. Embodied intelligence requires perception, planning, balance, touch, motor control, and enormous quantities of experience. China can collect that experience in factories, warehouses, stores, and training centers, but viewers should remain skeptical of robot videos. A dance proves coordination, not useful autonomy. A carefully edited factory demonstration may depend on remote control, a prepared environment, repeated attempts, or a narrow task. Humanoid robots remain expensive, energy-limited, maintenance-intensive, and less reliable than humans in unpredictable settings. The near-term future is probably not a robot that can do everything. It is a robot that performs a few valuable tasks in a controlled environment, learns from data, and gradually expands its range. China's manufacturing advantage may allow that gradual improvement to happen through thousands of machines rather than dozens of prototypes. All of this intelligence requires computing power. Advanced AI chips remain China's greatest strategic weakness. American export controls restrict access to leading processors and semiconductor manufacturing equipment. Chinese companies can still train powerful systems through efficiency, older or modified hardware, stockpiles, and large clusters. But constraints affect cost, speed, and experimentation. China's response is full-stack substitution. Huawei is developing Ascend processors, servers, networking, and large computing clusters such as its Atlas Super D systems. Other domestic chip companies are building alternatives for training and inference. Cloud providers are adapting model software to Chinese hardware. The challenge is not merely producing a chip with an impressive specification. NVIDIA's advantage includes software, developer tools, libraries, networking, and years of optimization. A domestic accelerator may perform well in theory, but lose efficiency because software cannot use it fully. Moving a model from one hardware ecosystem to another can require deep engineering. Large clusters also consume enormous electricity and water for cooling. If China compensates for weaker individual chips by connecting many more of them, communication overhead and energy use become critical. This is why model efficiency matters as much as model size. Sparse architectures, quantization, improved attention, better data, and more efficient inference are not secondary technical details. They are ways of turning geopolitical constraint into engineering pressure. China's government does not want AI to remain a collection of chat apps. Its AI Plus strategy aims to integrate artificial intelligence across manufacturing, science, communications, education, healthcare, agriculture, public services, and consumer products. In 2026, official plans placed particular emphasis on agents, collaboration between large and small models, intelligent networks, and wider access to low-latency computing power. The logic resembles China's earlier approach to high-speed rail, electric vehicles, solar power, and telecommunications. Coordinate policy, infrastructure, local governments, capital, universities, and companies then use a huge domestic market to accelerate deployment. This can produce rapid learning. A model used in a factory encounters real scheduling problems. A medical system meets messy records. An agricultural tool faces weather, dialects, and unreliable connectivity. Deployment generates feedback that laboratory benchmarks cannot, but scale also multiplies harm. An inaccurate education model can affect millions of students. Automated management can intensify worker surveillance. A government agent can make public services efficient while reducing the ability to challenge a decision. Hospitals may adopt systems before responsibility for errors is clear. AI can improve productivity without distributing the benefits fairly. Office workers may be expected to produce more rather than work less. Entry-level tasks that train young employees may disappear. Creative workers may compete against systems trained on their work. Older people and rural communities may face services designed around technology they cannot easily use. The success of AI Plus should therefore not be measured only by adoption rates. It should be measured by whether systems improve human capability, public accountability, safety, and living standards. China is promoting AI while regulating it aggressively. Rules require providers of public generative AI services to address security, personal information, and prohibited content. Measures for labeling AI-generated material took effect in 2025, and regulators have since punished platforms for labeling failures. In 2026, short video platforms were told to make AI-generated or fictional material more clearly identifiable. Some of this addresses universal problems: fraud, impersonation, deepfakes, misinformation, copyright, and undisclosed synthetic media. But Chinese AI governance also reflects the country's political system. Models available to the public operate within censorship requirements and restrictions on politically sensitive content. Companies must balance capability with compliance, sometimes producing refusals, incomplete answers, or different behavior inside and outside China. This creates two competing narratives. One says China is moving faster because it regulates practical harms while supporting innovation. The other says state control limits open inquiry and builds AI into a larger system of information management and surveillance. Both dynamics can exist at once. Trust will depend not only on whether an answer is accurate, but on whether users understand what data the system collects, which rules shape its responses, who can audit it, and what happens when it causes harm. The first global impact is price competition. Chinese models force American and European providers to justify premium prices. Even companies that never use a Chinese API benefit when competitors reduce costs or improve cheaper tiers. The second impact is access. Open-weight models allow startups, universities, and governments to build AI systems without depending entirely on a few closed platforms. This may accelerate local language AI and sovereign infrastructure across the global south. The third impact is a shift from national champions to ecosystems. The AI race is often described like a medal table. America versus China, GPT versus DeepSeek, one benchmark score against another. But modern AI depends on chips, energy, data centers, software, researchers, manufacturing applications, standards, capital, and trust. No country leads every layer. The United States retains major advantages in frontier chips, foundational research, global cloud platforms, and highly capable proprietary models. China has strengths in engineering scale, manufacturing, deployment, cost reduction, and increasingly competitive open weights. The fourth impact is pressure on the meaning of open. If Chinese firms become the main suppliers of downloadable frontier models, Western governments must decide whether to embrace them, restrict them, audit them, or invest more heavily in domestic alternatives. The result may not be one global AI ecosystem. It may be connected but politically divided stacks, with different chips, clouds, models, standards, safety rules, and information boundaries. China's latest AI developments tell a story larger than any model release. Kimi K3 shows that open-weight systems can approach the frontier at enormous scale. DeepSeek V4 shows how efficiency and low pricing can turn intelligence into infrastructure. MiniMax H3 shows text, image, video, and sound merging into one generative medium. National agent standards show AI moving from conversation toward coordinated action. Humanoid robots show the boundary between software and manufacturing beginning to dissolve. And domestic computing projects show China trying to build the entire stack under technological pressure. None of these systems is magic. Kimi K3 can still hallucinate. DeepSeek's low prices do not eliminate the cost of infrastructure. H3 cannot reliably direct a feature film. Humanoid robots cannot enter an ordinary factory and master every job. Domestic chips do not instantly replace NVIDIA's hardware and software ecosystem. The gap between a demonstration and a dependable product remains enormous. But China does not need every experiment to succeed. Its advantage may come from running many experiments at once, deploying them into a huge market, manufacturing the hardware, lowering the price, and improving through use. The most important question is no longer, can China build a model as capable as America's? In some categories, the answer is already close enough to make the question outdated. The new questions are harder. Can agents be trusted with real authority? Can open weights remain innovative without making dangerous capability impossible to control? Can robots become economically useful rather than spectacular performers? Can China overcome chip constraints without creating an energy crisis? And can the productivity created by AI improve ordinary lives rather than concentrating power in companies and states? The next phase of AI will not be decided by the chatbot with the most impressive answer. It will be decided by the systems that can act reliably, operate affordably, integrate with the physical economy, and earn enough trust to become invisible parts of everyday life. That is the race China is now entering. Which Chinese AI development should we examine next? Kimi K3, DeepSeek V4, MiniMax H3, humanoid robots, or China's domestic AI chips? Tell us in the comments. If you enjoyed this video, subscribe for more clear, balanced explanations of the technologies reshaping China and the world. Thanks for watching.